Welcome to Lesson 15A, Electrostatic Precipitators. Electrostatic precipitators, or ESPs, are a kind of APCS, air pollution control system, but they do not use inertial impaction, one of the few that do not. The only other APCS that didn't use inertial impaction was gravimetric settling, for example, electrostators. So how do they work? Well, there's a corona wire that charges particles as they pass by. There are some that charge particles positively and some that charge particles negatively. Either way, what happens then is the particles veer towards or are attracted to an oppositely charged plate, which we call a collector plate. And those particles will stick there when they hit. These collector plates are either opposite charge from the corona wire or they're grounded. If you have a large negative voltage, for example, on the corona wire, your collector plate can be a positive voltage or ground, which is 0 volts, and it would do the same thing. It would attract those particles. Here's a schematic of the kind that charges the particles negatively. Here's our corona wire, these red circles here. There's a whole bunch of them in between collector plates. In this case, the collector plates are charged positive, the corona wires are charged negative. We have dirty air coming in from the left, clean air out to the right, C out and C in or C not, as we usually do. In this particular case, there's flow straighteners. Sometimes there's also a filter to catch some of the big particles. Now, these corona wires can be charged to thousands of volts, and so any little particles that pass around them also get charged. So these little particles now become, in this case, negatively charged, and they're attracted to these positively charged plates. And so the particles start building up on these plates. Here's another kind where the wires called ionizer wires are charged positively. I show a close-up of a particle that gets charged positively. In this particular design, there are both positive and negative collector plates, the idea being that the positive plates repel the particle and the collector plates attract the particle, and so the particle tends to move towards the collector plate even faster. Sometimes there's a little hammer mechanism that goes back and forth and beats against these plates to dislodge the particles when you want to clean them. You turn off the voltages and then bang on these plates. One important thing in all these diagrams, we're looking down from the top. These plates are typically mounted vertically, so gravity is not an issue. And then when you pound on the plates, all those particles will just fall to the floor of the ESP and then be collected in some kind of hopper. This particular one also has a pre-filter and an after filter. The pre-filter might be a disposable paper filter to collect big particles. The after filter might be a HEPA filter or some kind of charcoal filter to get rid of odors and stuff too. Some terminology to the side here. A negative charged plate or wire is called an anode, and a positive charged plate or wire is called a cathode. Here's a three-dimensional diagram of an ESP. Here we have negatively charged corona wires, and these represent the particles that get negatively charged as they pass near the corona wires. And then the plates are positive, they're cathodes. And so the particles will get attracted to the plates. Here's an actual grade efficiency curve of a particular ESP. There's a few outliers here, I'm not sure why, but it tends to have this S-curve type shape, except at very small particle diameters, it starts to veer back up. So again, we have the same kind of thing. We have diffusion here, and then here, instead of inertial separation on the right, we have the ESP attraction that dominates. Notice that there's still a dip in the efficiency curve. This one's about 0.4 microns. So that's a little bit different than the filters, which are typically around 0.2 microns. And notice that even though it has a dip, it's still around 90% efficient even at the dip. So if you put a filter in series with an ESP, you'll have your dip of the filter like this, and you'll have your dip of your ESP like that curve. And when you combine the two, you can still get pretty good efficiency for most particles. Sometimes you'll see these ceiling-mounted ESPs in restaurants and other public places. This is a vendor ad showing that they have a 2-stage electrostatic precipitator that removes smoke and fumes and small particles. These are also used for removing welding fumes when welding indoors. You don't want to be breathing those welding fumes. Indoor ESPs are usually positive ionization, meaning that particles get positively charged. These produce less ozone. That's why they're used indoors. Whereas outdoor ESPs, which are usually bigger, used for coal power plants or kilns or something like that to clean dusty air, can be either plus or minus ionization, but from what I've seen, they're usually the negative ones. So ozone one is really the only reason why you would do one versus the other. Let's do a quick analysis of ESPs. I'm going to do this by way of an analogy. This is actually a very cool analogy of something we've talked about previously. So I'll draw a line right down the middle. On the left will be our ESP, and on the right will be gravimetric settling in a duct. Keep in mind that with the ESP, we're looking down, whereas with the gravimetric settling, we're looking from the side. And obviously, gravity is critical for gravimetric settling. But if you think about it, they look similar. Remember, we talked about gravimetric settling in some kind of a channel of length L and height h. And we have an airspeed u. What happens is little particles fall at some settling speed, little v, and so the particles veer down and hit the bottom plate and are collected. Well, we'll draw a very similar thing for ESP, except let's use the center line as the top and one of the plates as the bottom. So here's our collector plate. If we go back up to this diagram, we're considering just one section of this midway between two plates. So we have particles that veer towards the plate. The math is the same whether these are positive or negatively charged. So we have a very similar situation with a U and an H, and we have the air moving along at capital U, and we have the particles veering down at some speed, which we're going to call W. This is the center line. So in the gravimetric settling case, V is the settling speed. In the ESP, W is the drift speed. It's also called the migration speed, with the idea that these particles migrate towards the collector plate. I use this symbol to mean analogous. These are very analogous to each other, except instead of gravity on the right, we have electrical forces on the left. Now we use the notation capital VT as the terminal settling speed for the gravimetric settling. So let's do a similar thing we're going to call WT, the terminal drift speed. We achieve VT when F gravity equal F drag. So remember drawing this particle with a gravity force down and drag force up. We have exactly the same situation on the left here. Instead of gravity, we have some electrical force down and a drag force up. And either way, when those two balance, F electrical equal F drag, just like here, it's F gravity equal F drag. And then we were able to generate an equation for VT for the gravimetric case. We want to do a similar thing for WT here. We can do that, but we won't do that simply because we don't have time. And also, it gets very complicated, and we usually end up doing experiments anyway. The bottom line is that we got a grade efficiency, which was 1 minus EXP negative L over LC. That's for the well-mixed case, where the critical length LC was HU over VT. Well, since these are so analogous, we expect the same equations. And indeed, we get the same equation for grade efficiency, where the critical length is now HU over WT instead of HU over VT. This is really cool because they're pretty much the same thing going on. Dude, thanks for the cool analogy, man. You're quite welcome, Joe. Well, this is where we stopped with the gravimetric settling, and we're able to predict all this stuff analytically. For ESPs, it's hard to determine WT. This is my analogy, but what most people do in the textbooks and stuff is to rewrite in terms of Q, which is volume flow rate. Q is U times H times capital W, where W is the width of the channel or the plate into the page. Again, looking at our diagram, it's the dimension into the page. By the way, this is the center line, so the same thing's happening as a mirror image around the center line on another plate that's up here. So all we need to be concerned about is half of the channel. Instead of calling that H over 2, I called it H. So we make this good analogy here. We rewrite this in terms of Q, volume flow rate, and another parameter, which is AS, which is the total surface area of the plate, one side only. So again, for our single channel, we have this center line and the plate. So this surface area, AS, is W, again, the width into the page, times L, where L is the length of the plate. So let's do a little bit of algebra with this equation. Our grade collection efficiency, let's plug in LC in the denominator. So this gives us negative WTL over HU. I multiply and divide by capital W, the width of the plate into the page. And now I recognize this as AS, and I recognize this as Q from here. So I rewrite this rearranging as 1 minus EXP negative WT AS over Q. Now this was all for just one channel. of distance between center line and plate H. But you can make some simple argument that both Q and AS grow linearly with W and grow linearly with multiple collector plates in parallel. So though we're analyzing one unit here, one kind of section of this ESP, we're analyzing this one unit, but there's a whole bunch of these in parallel. There's also a whole bunch of these in series, but that is accounted for by the total length L. So just think of these in series as one longer plate L. The point being that this equation we derive for one of these little sections doesn't change when we're analyzing the entire ESP. Therefore, here's our summary set of equations. We have eta, grade efficiency, is 1 minus EXP negative WT AS of all the plates over Q of the whole ESP. So it's the same equation we had here, except now we're using AS, the total surface area of all the collector plates. That will include both sides, since we're collecting on both sides of these plates. And then QESP is the actual total volume flow rate through the ESP, whereas Q and AS were just the values for that one section. Notice that this is actual flow rate. So if you're doing English system ACFM, not CFM, make sure you know that. Well, what about WT? How do we get that? There are some equations, but in this course, quizzes, homework, etc., WT will have to be given, or it will be the variable we solve for. So that's our main equation, and now we're ready to do an example problem. This is a very practical example based on a real ESP. This ESP is used to remove lime dust particles from a lime kiln. By the way, this WT will depend also on particle density and size and temperature of the air, viscosity, all that stuff. There's even Cunningham correction factors for very small particles because we're doing the drag coefficient. It gets very complicated. There are also tables out there that give you W for various kinds of particles in various applications. For this particular case, WT, the migration speed, is 1.50 centimeters per second. The data I found for this particular ESP were in English units. The total collector surface area, AS, was 112,000 square feet, and the QESP was 73,120 ACFM. So it's in the right units. If it were in SCFM, you'd have to convert that to ACFM using the equations we learned in the first week of class. This is just a matter of plugging in and doing some unit conversions. 1 minus EXP to the negative WT, AS of the plates, QESP, CFM is cubic feet per minute, remember. And then I'll do a bunch of unit conversions and close our bracket. Everything inside that EXP bracket must be non-dimensional. And so we have to make sure all these units cancel. I plug that in our calculator and I get 0.9891. So the grade efficiency for these particular particles is about 98.9%. And you can plot eta of dP versus dP as a grade efficiency curve, as we've been doing for all our other APCSs. Generally, it may look something like that, like we've seen for filters. There's an S curve, but because of diffusion effects, it tends to go back up again for smaller particles. By the way, it is possible to have two cut diameters if this curve dips below 50%, but these things are usually very efficient, and so it never dips below 50%, so you never have a cut diameter. Ideally, these are designed so that they're in the 90% for all particles. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.